Good morning, Professor.
Hey there, how's it going?
Pretty great. How about you?
I'm hanging in there. So Carly asked, the test opens on the 31st. Yes, that is correct. I haven't tried to click on the module yet because I am scared I might mess something up. No, you should go ahead and click on it now. There's a couple pieces of information you can read about. You won't, once you click on that page, you won't be able to do anything further until 11 a.m. on the 8 a.m. on the 31st when it actually does open. So let me open my share screen here. And I'm going to move that over there. So I want to share that. So at this point, you guys should see the slide deck for today. So I want to do just a brief tour of Canvas because I'm getting a lot of emails about where to find things. And a reminder of some upcoming deadlines. Then we'll go through the molecule of the lecture. We'll look at some functional group identification worksheets, which those were posted in Canvas. And then hopefully we'll get to the workbook stuff today as well. So let me stop sharing. I'm going to share a different screen now. And that screen should be this. So hopefully you can all see my Canvas module or Canvas screen now. Okay, so let me go to just this real quick. I'll take about 5 minutes to do this. So this should be like your home landing screen. The syllabus is here as a PDF. Now, if you click that, again, depending on what your computer is, what your browser is, that might either just download or it might download and launch it in your PDF reader. So that's completely up to how your system is set up. So why is it asking me if people can join? It's asking everyone that, Blakely. Basically, the people that are shown in the meeting chat as guests, I think you need to download the app so that you can get right into the meeting rather than being in the waiting room. So the course summary, again, these are dates. These are the details of the either assignments or things like the chat. So there's, again, you need to pay attention to these times. So to do versus due by. So I guess we can go through this right now. So Monday, August 31st, homework 1, homework 2, those are both due by 11 a.m. Again, pay attention to the AM, PM. Your index of learning styles for 3 points, that's 11 a.m. Orion 1 and 2, so all this stuff's due by 11 a.m. Your exam 1 is going to open August 31st at 8 a.m. and then it closes Tuesday, September 1st at 8 a.m. So the window is open for 24 hours, but once you start it, you only get 60 minutes to complete it. So for Carly, you need to, for the index of learning styles, so if you go down to the assignments, engagement, and professional activities, if you click on that, that should launch the page. And again, yours is going to look different. You take this survey, then you upload the screenshot, and then I'll look at it and give you your 3 points. So what I want to show you guys is just a brief tour of how this is laid out. So if you click on your modules, presumably you got into this chat by clicking this link. So I really encourage you to click through all of these pages. So again, there's tutorial center information. If you click on here, this is an online sign up that you can reserve time with chemistry tutors. So if you click and start here, these are 3 videos that I've posted about how to navigate Canvas for this course in this semester. And so this is the Canvas tour, this is the syllabus tour, and then I did another Canvas tour of the Wiley Plus resources. So I've been getting quite a few emails about how do I find the chapter readings. So again, in your Module 1, the Module 1 synopsis, this is what you're learning in this synopsis, or in this module, this is the synopsis. This is your chapter readings. These are the learning outcomes. These are the assessments. This is the 2-week schedule for this module. And the screencasts that you should be watching, this is the stuff, if we were meeting face-to-face, that I would be teaching. You should be watching these screencasts, so you should be caught up. So go through and watch these screencasts for the formal lecture materials. So all I did was click next. We're still in that same module. These are the team chat recordings. They're posted here according to the date. I'm going to click next again. So let me just go back so you visually see that. We're in module 1. See this right here? This is the link to the chapter 1 reading in Wiley. So I'm going to click that. Now see how the mouse changes from the arrow to the hand? Now I'm going to click that, but I have to share a different screen now. So at this point, you should all see it launched chapter 1 in your book for Wiley Plus. So this is the online textbook. You can navigate this 2 ways. Here are the chapter subheadings. So you can click here, you scroll down, or you can hit next. So these problems you see, if you sort of work them in the textbook reading, that's fine, but you're not getting formal credit for them because you have to launch the separate homework link in Canvas. The problems in the homework set are picked exactly from this textbook. The Orion sets are different questions that are not embedded within the text. So for example, I'm going to click that. I guess you can't see it because it launches a different window, but basically these things should look familiar to you in the homework sets. So there's these other resources as well, and that's really what, if you click here, it'll launch a different window, and that's what you're paying for the required course fees, is not only this course textbook, but the access to Wiley Plus homework, and then these other resources, which are videos, solved problem videos, reaction explorers, multimedia content. So you get all this stuff. It's really up to you how much time you want to spend on that. So I'm going to stop sharing that. Let me reshare the Canvas window. So again, right now you should only be able to see the Module 1 stuff. This is your chapter reading. There's the homework. There's the Orion chapter, Orion homework. So if I click Module 1 exam, Here's some blurbs about it that you can read, and then when it opens, you'll actually see the link, and you need to download the Respondus lockdown browser because that's how you take the exam is through that browser. So any questions on the Canvas tour? So let me share this. So we're back in the slide deck. Hopefully everyone can see that. So in preparing for your exam 1, again, which opens Monday at 8 a.m. Once you click on it and you start it, you have 60 minutes to finish it. The exam's going to be 25 questions of various types that you've already seen in the homework, and it's worth 100 points. So I like to show this slide because Lord Baelish's quote here, you can read it, I won't repeat it, but I think what organic chemistry is going to do is challenge you like you've never been challenged before. So in something new, you always have to grow, right? So you should not consider this course as a continuation of Gen Chem, where you're sort of doing the same thing. You're doing very different things, and you have to be very mentally adept to learning those things and applying those things. So Lord Baelish is basically saying prepare yourself in as many different ways as you can, and don't be surprised by anything. Do the readings, do the homeworks, and you should have no issues when you take the exams. The exam opens Monday morning at 8 a.m. and it closes Tuesday morning at 8 a.m. Does the exam work with iPads? I'm checking on that. I do not know the answer to that just yet. Any further questions before we move on to our molecules here today? Again, I encourage you to download that lockdown browser today to make sure that it works, because you don't want to be finding out sometime Monday that it doesn't work and having to panic about that. So let's go ahead and move on. We saw this molecule Tamiflu in the last chat session. Again, here it is. It's the common name is oseltamivir. Sold by Roche as Tamiflu. Here are the pills. What I want to do today is identify the functional groups present in this molecule. So here's the slide that was uploaded into Canvas as a PDF. And what I want to do is spend some time, if you can download that file, either have it open or print it out. Let's go through and identify in these boxes what these arrows are, what functional groups these arrows are pointing to. So Mac is asking about testing the lockdown browser. I'm not specifically sure if it will launch without the presence of the exam being open. So we'll have to go check that Word document that was uploaded. I'm pretty sure that if you have it installed, it should work seamlessly once that exam period opens. So again, remember the questions that I asked you in the last chat session. I asked you about sp3 hybridized carbons, sp2, how many hydrogens were on each, what's a methyl group, what's methylene, what's methine, etc. So what I want to do now is we're looking at the same molecule. Now let's identify these different subsets of bonded atoms called functional groups. So in this box here, this arrow is pointing to this oxygen. This oxygen is bonded to a carbon and a carbon. So carbon, oxygen, carbon is what sort of functional group? You can write your response in the chat. So we have some fast responders here. They're calling it an ether, E-T-H-E-R, ether. So yes, that is an ether functional group. So I'm just checking, I'm uploading another screencast into YouTube. That will be the last one for Module 1. The internet's choppy, so it didn't upload yet. It will be there in a couple hours. So what about this functional group here? We have a carbon-carbon double bond. What's that called? So it's called an alkene, A-L-K-E-N-E, alkene. So again, what we are doing in Module 1 is we're learning how to communicate structure. So when I tell you the alkene of Tamiflu undergoes this transformation, in your mind, you should be picturing a carbon-carbon double bond when you hear the word alkene. So this box is pointing to a carbon that has a double bond to oxygen, a sigma bond to oxygen, and then this oxygen's bond to carbon. So we're concerned with these 4 atoms here and how they're connected. What is this functional group called? So yeah, it's called an ester, E-S-T-E-R, ester. So again, an ester is different from an ether. And again, there's the words ester, ether, and you should be able to visualize how these atoms are bonded. That's a functional group. So we've learned ether, alkene, ester. Those functional groups all have different reactivity. Now this box is pointing to this. How would you classify this carbon? What would you call it? So it is a methyl group, and a methyl group could be called, what's like a more general name for a methyl? An sp3 hybridized carbon. Yes, it's an alkane. A-L-K-A-N-E. So alkane, alkene. Again, it's subtle. The consonants, the vowels change a little bit, but they mean different things. Now this box is pointing to a nitrogen. What are nitrogen functional groups called? So a nitrogen singly bound to a carbon. So that's an amine. So amine, A-M-I-N-E. Now what about this box? It's pointing to carbon-oxygen double bond. But now this is bound, sigma bound to a nitrogen. So this is called an amide. So notice the difference. See this CO pi bond? You have one there, you have one there. Really, when you're looking at a CO pi bond, you have to go out and see what else it's bonded to. This has oxygen, then carbon. This has nitrogen, then carbon. So this is an amide. So we have ether, alkene, ester, alkane, amine, amide. So think about that's 6 functional groups, right? Boom, 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 boom. So that's a lot of information. So what do you know so far? You know oxygen's an element. It's forming 2 sigma bonds. It has lone pairs. You know from the periodic table that it's more electronegative than carbon, so the bonds are polarized. The functional groups are basically giving rise to the physiological or physical properties this molecule exhibits and why it can be taken as a drug. So this slide here just shows you the answers that we just went through. So I don't have a QR code for this one, this molecule of the lecture. It's called rapamycin. This is the structure of rapamycin. It's called a macrolide, which basically means it has a very large cyclic structure. So rapamycin is isolated from Streptomyces hygroscopic on what is known as Easter Island or Rapa Nui. So Rapa Nui is the island. We basically call it Easter Island. You're probably familiar with these statues. So what scientists do, in particular, this scientist here, this gentleman, they will travel around the world and basically harvest soils from different parts of the world, soils on land or marine sponges underwater, and they'll do chemical extractions of those materials. And we as humans, as we've evolved through history, we found that plants produce things, and we call them natural products. And so rapamycin is a natural product. And it just so happens that it's in humans, the therapeutic indication is it's an immunosuppressant. So this molecule, which is found in the soil on Rapa Nui, is an immunosuppressant, and it's sold as Rapamune by Pfizer, either as a pill or it's coated on stents. When people get high cholesterol, the volume that can be pumped through, the volume of blood that can be pumped through their veins sort of decreases due to that cholesterol. So a stent basically holds that opening to a certain diameter or width. So as shown in this diagram, that's the stent, and it's been coated with rapamycin, and that basically prevents further sort of immune responses. So look at, there's a lot of functional groups present in this molecule, right? So even though it looks complex, we want to understand, these different bonding patterns. We have a lot of different type of oxygen, but they're in different functional groups. So let's do sort of the same activity. So in the box where the mouse is hovering, what functional group is that? So we have some responses. That is an alcohol. So let me type in here. So an alcohol has an OH group. there are three types or three classifications of alcohols. Look at this carbon. Does anyone know what type of alcohol this is? How would you classify that alcohol? So what I'm asking you is basically, so cyclohexanol, yeah, it would be a cyclohexanol. Really what I'm asking you is this carbon is bonded to two other carbons. So the carbon bearing the OH has 1, 2. So this would be called a secondary alcohol. So there's the word. You might otherwise see the number, like secondary with like a degree sign. So secondary. Maybe this time let's go counterclockwise. So what functional group is this? So Elizabeth says, yes, there are three classes: primary, secondary, and tertiary alcohols. The functional group shown, that is an ether. Again, we have carbon, oxygen, carbon, that's an ether. Moving down to this one, we're pointing at this carbon now. What is this functional group? Again, so Rosemary and Hannah, we have a CO pi bond, so we have a carbon-oxygen double bond, but now it's bound to nitrogen. So we have some revision of answers here. Yeah, it's an amide. So there are three types of amides. When we're considering the nitrogen, it's bonded to 1, 2, 3 carbons, so it's an amide. It's bound to 3 carbons, so this is a tertiary amide. So tertiary amide. Now this functional group here, we're pointing at that carbon. What would we call that functional group? So Elizabeth is asking, the classification is dependent upon the number of carbons. Yes, for an amide that is true. All you're doing is counting 1, 2, 3. So this is an amide, and because there's 3 carbons, it's called a tertiary amide. So Christina, we're actually pointing to this carbon right here. So a carbon bearing a single CH, yeah, it's sp3 hybridized. Yeah, it would be tertiary, so it's a methine. So it's an alkane. It's a tertiary carbon. And methine. So there's all these different sort of things we can classify it as. So now in this box here, we're pointing to a different type of carbon. What would you call that one? Obviously, it's sp3 hybridized. It's an alkane. How would you classify it? The tertiary and methine are sort of the same thing if you're referring to the carbon. So the one that this one is pointing to What would we call this one? It's not tertiary anymore. Yeah, it's secondary, so it's methylene. So moving now, we have a carbon-carbon double bond. So we would call this what? So yeah, it's an alkene. So now this is pointing to an sp3 hybridized carbon, so we would call this one what? So it's a methyl group. We could also call it primary. Now this box is pointing to a carbon doubly bound to oxygen. Notice what it's bound to, carbon and carbon. So what is this? We haven't named one of these yet. So that's called a ketone. Blakely, I'm not sure how to accomplish what you're asking in the chat. Again, I'm not real savvy on a lot of this stuff. Maybe someone can help Blakely out with her question there. So let's if we're here, what about this carbon here? What is this functional group called again? So yeah, it's an alcohol. So the hydroxyl group is the OH. The functional group is alcohol. If you count the number of carbons bound to that carbon, how many do you have? How would you classify that alcohol? So it's secondary. We have 1, 2. Sarah's asking, why is this ketone not an ester? Can anyone explain why this is a ketone and why it's not an ester? So if you look at the connectivity, this carbonyl group, so a CO double bond, I'm going to use that word quite a bit, C. That's referred to as a carbonyl, much like C is referred to as an alkene. This carbonyl has carbon-carbon. If you look over here, this carbonyl has carbon-oxygen, and then that oxygen's bound to carbon, so that's an ester. So yeah, it's, Sarah, to get to your point, it's, again, organic chemistry is going to challenge you in the sense that you have to see the big picture, but you also have to see sort of up close. So like with that Lord Baelish comment at the beginning, you don't want to get, hit by a train because you're not paying attention to like a certain part of the molecule or whatever. So you need to see the big picture, but also be cognizant of the smaller connections as well. So we said this was a ketone, this was a secondary alcohol. This one right here is a ketone as well, because it's carbon-carbon. This is an ester. We have carbonyl bound to oxygen and carbon, but this oxygen is also bound to carbon. Before we go on to some more questions, the screencast that I'm going to upload today, I also talk about another thing called oxidation state, which I briefly want to cover on this slide. Because I think it helps. I'm not going to use the word memorize because I just don't like the word memorize for organic chemistry. Maybe the term associate, make an association is better. I want to say that an alkane carbon, so this carbon I'm pointing to here, I want to say that sp3 hybridized carbon has an oxidation state of 0. And what I mean by that, it has a carbon-carbon bond and then 3 carbon-hydrogen bonds. An alcohol has an oxidation state of 1. So here's an alkane. I'm going to say that oxidation state is 0. Here's a carbon bearing a hydroxyl group. So this is called an alcohol. I'm going to say that carbon has an oxidation state of 1. And all I am doing, I am counting this bond, the bond to oxygen. Oxygen is a heteroatom. Heteroatoms are things that are not carbon or hydrogen. So nitrogen, oxygen, sulfur, fluorine, chlorine, bromine, iodine. Those are heteroatoms. All I did when I said that carbon's at an oxidation state of 1, I counted the number of bonds to a heteroatom. It's 1. So I posted a question in the chat. This carbon here of the ketone, it's at oxidation state what? Type a number in the chat box. What do you think it is based on that logic? So it's oxidation state 2. So what about this carbon here? We said that was an ester. So Rosemary got her fingers a bit too fast on the keyboard, I think. So it's an oxidation state of 3. So to sort of circle back to what Sarah was asking about, why is one a ketone and another's an ester? So to help you like categorize these functional groups, so look at this carbon and just count the heteroatoms. 1, 2. You're counting the bonds. That's 2. So oxidation state 2 functional groups. There's either an aldehyde or a ketone. Oxidation state 3. We have 1, 2, 3. So this ends up being an ester. So look at this one. 1, 2, 3. That's an amide because that's now nitrogen. 1, 2, 3. So the way that I teach this may differ slightly from your book, and I hope that doesn't upset you. because I believe that the way that I teach oxidation state analysis is as simple as it can be. All you are doing is counting the bonds to a heteroatom. So again, this carbon is 0. This carbon right here is 1. There's 1 bond. This is 2, 1, 2. This carbon is 3, 1, 2, 3. So Columbia is asking about oxidation state 2. So I'm going to say OS2. Functional groups are aldehydes or ketones. It just so happens that this molecule does not have an aldehyde in it. So so we said this was an oxidation state 2 functional group, ketone. How does an aldehyde differ? You would have a carbon, and then this bond would be to hydrogen. So Elizabeth, basically you're counting the bonds. So let's look at the ester. So this ester right here has 1, 2 oxygens bonded to it, but you have to count the bonds. You have 1, 2, 3. So yes, you're counting the number of bonds, not the number of heteroatoms. And so the reason I teach it this way, so as Mac asks, yes, you're just counting heteroatoms. You don't count carbon or hydrogen. So I'm going to upload a screencast after the video renders, and it will sort of look like this. Basically, we're increasing oxidation state from 0 in alkanes to 1 in alkyl halides, 1 in alcohols, 2 in aldehydes and ketones, 3 in acids and their derivatives. So I'll sort of pull back. You can see it's a pretty busy slide. What's presented in that slide is how I like to teach this subject, because as you learn reactions, I want you to look at a carbon, identify the oxidation state, think about the functional group, and think about the transformations that can happen on that carbon. So if you think in a very logical manner, to me, it reduces the mental burden you have of having to memorize things. If you understand the concepts, you don't have to memorize. You can just think your way through it. So, Katie, are you asking about this one right here where the mouse is pointing? So this one, if we look at that carbon, we have 1, 2 bonds. The oxidation state is 2. We have carbon, carbon, so this is a ketone. So here it is with the answers populated. So that's a ketone. So as you learn these oxidation states, 0, 1, 2, 3, you'll see that the functional groups can be categorized in them differently. So notice on here, there's no oxidation state 4. If you think about oxidation state 4, can you think of a molecule where a carbon could have an oxidation state of 4? You can either draw or write the formula in the chat or write the name. A carbon that has 4 bonds to heteroatoms. So Garima CH4 That's an oxidation state of 0. That's an alkane. Aden has one, carbon dioxide, CO2. So as the chat will allow me, here is a Lewis dot structure of CO2. So look at CO2 there, and you can count the bonds to heteroatoms. There's 4. What is the hybridization of that central carbon in CO2? So Garima, Aden, Mac all say SP. It is SP. So Mac wrote up there carbon tetrahydroxide. Yes, the oxidation state of that carbon is 4. That is correct. In that molecule in particular, the hybridization would be sp3. So you can see that there's functional group equivalency between carbon dioxide and what Mac proposed as carbon tetrahydroxide. So really, what we hope to accomplish over this first module, like I said, is how to communicate structure. So let's ask some questions here. Again, this is a visual inspection. Here's rapamycin. How many pi bonds and how many rings do you see? So maybe for this one type of letter, since you have sort of 2 columns you need to choose in. So you might, there are definitely 9 pi bonds. That is for certain. But there are not 3 rings. So remember what I said about like not getting railroaded by focusing too much on one thing? So Rosemary points out there are 4 rings. So the correct answer is A. How is that? There's 1 ring, 2, 3. And then look at this. This whole thing right here is a ring. That's a large ring. So that's called a macro cycle. So your eyeball is probably immediately drawn to these smaller rings, right? But don't lose fact that there's a giant ring in there. So the pi bonds, you're counting 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's another question. We sort of already answered this one, but let's, in the chat box, type a letter. Again, if you were taking the exam face-to-face Monday, this would be a type of question that I would write and you would see on the exam. So the Roman numerals 1, 2, 3 are pointing to different functional groups, and it's asking you 1, 2, 3. How would you classify those functional groups? So yeah, it looks like C is the correct answer. We have an ether, we have a ketone, and we have the ester. So this next one doesn't relate to rapamycin, it's just a general review. And it's asking you which of the following choices is incorrect in relation to classifying hybridization versus the number of sigma bonds and pi bonds for that type of hybridization. Which one is incorrect? So the correct answer is D. D as in dog. This is incorrect because an sp3 hybridized carbon has 4 sigma bonds and no pi bonds. So again, just look at the trend here. sp3, 4 sigma bonds, 0 pi bonds. sp2, 3 sigma bonds, 1 pi bond. sp, 2 sigma, 2 pi. So we have about 10 minutes left, and what I would like to do is, wouldn't D exceed the octet rule? Ketonia is asking. Yeah, there might be something funky happening with molecular orbitals if you try to propose something like that, I guess. What I would like to do now is I'm going to stop sharing. I'm going to flip this on. So can you all see the document camera now? The document camera is now on the workbook, and it has the focus level quite small. Let me see if I can get it closer. How do I make it take up the whole screen? Aiden says click on it. Click it or pin it. Whoop. Sorry about that. So just let me know if it gets out of focus. But this is page 9 in the workbook, chapter 1. It's section 1.5, identifying formal charges. Exercise 133, it says, consider the nitrogen atom in the structure below and determine if it has a formal charge. So you've probably already encountered this in your reading and your problems. So far, everything we've seen, there's been, the atoms have been in their neutral, I'm going to say neutral state of 0. So what does that mean? I want to say normal bonding pattern. So if we look at this nitrogen here, normally when we see nitrogen, it has, I want to say, sorry, I got to keep moving this. So nitrogen normally has how many bonds? So Mac got it right. It normally has 3 bonds, and then how many lone pairs? One. So a normal nitrogen will have 3 bonds, 1 lone pair. When we look at this nitrogen here, it has 4 bonds. So maybe I can put another thing here. We'll say formal charge 0. So this nitrogen has 4 bonds. It has no lone pairs. So as some people have already stated in the chat, it's going to have a charge of +1. So how do we get to that +1? So again, this is not a neutral nitrogen because it does not obey this bonding pattern of 3 bonds, 1 lone pair. So the charge is +1. How do we determine that? Formal charge. So the way that I like to remember this, and again, your book will probably teach it a little bit different. So I like to take the group number. So nitrogen is in group 5. Then we're going to subtract out 1/2 of the total bonding electrons. We have 2, 4, 6, 8 bonding electrons, minus the number of lone pair electrons. There's 0. There's 0 lone pair electrons. So we have 5 minus 1/2 of 8 is 4. 5 minus 4 is equal to +1. So that's how we got that number. So Garima's asking, can you use a different formula? Yeah, I mean, it's presented in a lot of different ways. This is just the way that I like to remember doing it. I think it's the most straightforward. So formal charge is equal to the group number minus 1/2 the bonding electrons minus the number of lone pair electrons. So let's do some more of these. So let's do 134. So this is asking specifically only for oxygen or nitrogen. So look at this oxygen right there. What is the normal bonding pattern for oxygen? The normal bonding pattern, number of bonds, number lone pairs. For oxygen, it's normally 2 bonds, 2 lone pairs. So if we look just visually, we have 1 bond, 2 bond, 2 lone pairs. The charge on this oxygen is 0. But how can we calculate that? So formal charge, oxygen is in group 6 minus 1/2 the bonding electrons, so there's 2, 4. Then minus the total number of lone pair electrons, we have 1, 2, 3, 4. So we have 6 minus 2 minus 4, so that gets us to 0. So visually, when we look at it, we can see it should be 0, and then this is a way to calculate it. What about 135? Now look at this oxygen. Does that look like its normal bonding pattern to you? It should not, because we said this is the normal bonding pattern. 2 bonds, 2 lone pairs. So how do we calculate formal charge? Oxygen's group 6 minus 1/2 the bonding electrons, so we have 2, 4, 6 minus 1, 2 lone pair electrons, so that's 6 minus 1/2 of 6 is 3 minus 2, so 6 minus 5, that's +1. So you'll eventually do enough of these that you can just look at the bonding pattern and determine what the charge is. Let's finish off with one more, which is a nitrogen, 136. So the formal charge on this nitrogen is group 5 minus 1/2 the bonding electron, so there's 2, 4, minus the unpair or the lone pair electrons, 1, 2, 3, 4. So Garima and James are sort of disagreeing. Let's just go through the math here. So we have 5 minus 1/2 of 4, so that's 5 minus 2 minus 4. So that's minus 6. 5 minus 6 is minus 1. So it should be minus 1. So again, you'll eventually look at enough of these structures so that you can visually say if it's in its normal bonding pattern. Then if it's not, if it's a +1 charge or a -1 charge or a +2 or -2. But this is the equation you would use to do that. Just to show you before we end, say you wanted that carbon, this methyl group. There's no charge associated with it, so how do we determine that? Carbon is group 4 minus 1/2 of the bonds. There's 3 hydrogens, so 2, 4, 6, 8. There's no lone pair electrons, so 4 minus 4 is 0. So the carbon is 0. So it's implicit, right? So we're about out of time for today. So just to recap, there will be a screencast posted in Canvas through a YouTube link on functional groups. Please start working on your homeworks and your Orion sets. In your exam 1 will open up on Monday at 8 a.m. Once you start it, you have 60 minutes to finish it. So if you have any questions, again, either start a discussion in Canvas or shoot me an email. But otherwise, have a good weekend, and I'm going to go ahead and sign off.